This video is about TCP congestion control, which is one of the key features of TCP. Congestion control cannot be found on lower layers and is also not implemented in UDP. On the first slide, we see an illustration of an example scenario. We have three computers that send data to a router with the aim to reach another computer. The problem is that data from all three computers has to be forwarded by the router on the same output port. If we assume that all links have the same capacity, for example 1 gigabit per second, then you see that we run into a problem if these three computers use their links to a large extent. If the situation is present for a short time, then buffering inside the router can help. However, after some time, the buffer will become too full and new packets will be dropped. One TCP feature that makes the situation worse is that TCP is a reliable protocol. TCP waits for an acknowledgement for each segment and resends segments if it does not receive acknowledgements. Therefore, dropped segments are sent again and contribute to the congestion. Maybe your first idea about this problem is that some kind of feedback mechanism is needed. An overloaded router should send notifications back to the data sources so that the sources send less data. However, this is not so easy because there are many data flows that traverse a router at a central location in the internet, and many of them are only short-lived. So there would be a lot of control data, and in addition, the router would have to do a lot of calculations. In general, it has often turned out to be a scalable solution to implement sophisticated mechanisms only at the network edge and to keep the core of the network quite simple. Therefore, TCP congestion control is only implemented in the end systems. The routers know nothing about it. An important parameter in the context of TCP congestion control is the maximum segment size, MSS. This value is determined at the beginning of a TCP connection. It is influenced by the operation system, but an important constraint is the maximum transmission unit on the data link layer. The MSS is selected in a way to make use of the MTU size as much as possible and to avoid fragmentation. On the bottom of the slide, we see an example of a TCP segment which is delivered by IP and Ethernet. Ethernet specifies an MTU size of 1500 bytes. The MSS is selected as the MTU minus the size of the IP header minus the size of the TCP header. The result is 1500 minus 20 equals 1460. So if TCP segments have a payload size of 1460 bytes, they completely use the maximum payload size of Ethernet, but IP fragmentation is avoided. On this slide, we see the basic idea of TCP's congestion control, which is called additive increase, multiplicative decrease. On the x-axis, there is the timeline given as x times the round-trip time. The reason for this indication of the time is that after the RTT, the end system can determine whether it has received acknowledgements for the previously sent segments. Actually, it has to be a bit more than the RTT, but this is a topic of another video. After the RTT, it is possible to react and to increase or decrease the data rate. On the y-axis, we see the data rate. It is indicated as x times the MSS. Now let us see how the method works. In the beginning, the data rate is increased linearly. The end system sends one segment with a payload length of 1 MSS. After getting an acknowledgement for the segment, it sends two segments and waits for acknowledgements. After the successful confirmation, 3 segments are sent. It is important that you understand now 3 segments are sent following each other as quickly as possible. It is not just a third segment. The data rate is increased up to a point where acknowledgements are missing. In such a situation, which you see indicated as loss on the slide, the data rate is bisected. This is the multiplicative decrease. The question is why the data rate is reduced in this significant manner. You can argument that maybe the previous data rate has been a bit too much, so that if you lower it a bit, then everything is fine again. However, once there are missing acknowledgements due to a network overload, buffers in routers are completely full. It therefore makes sense to send significantly less data, so that routers can forward previously buffered data. As a whole, TCP is adapting its data rate all the time. It tries to increase it and has to lower it after loss. The general point is that there is no coordination with other systems, so that each system has no idea which data rate is available. All systems that send data via TCP use this mechanism independently from each other. When we do a simple calculation that you see on this slide, we find that the additive increase can take a relatively long time until a high data rate is reached. This is not appropriate because many TCP connections exist only for a short period of time. Therefore, the idea is to do it differently by using the slow start mechanism. Its approach is to do an exponential increase of the data rate. This means that you start to send one TCP segment. After its confirmation, you send 2 segments, then 4, 8, 16 and so on segments. In this way, you learn much quicker which data rates are possible for the connection. That is, whether it is maybe just a few hundred kilobits per second or several hundred megabits per second. Here we see an example where the slow start mechanism is included. At the beginning, a slow start is performed until a predefined threshold. After the threshold, the data rate is increased linearly. Once acknowledgements are not received as expected, there is again a slow start. The new threshold for it is half of the previous data rate. The TCP implementation on the previous slide is called TCP Tahoe. Its improvement is named TCP Reno, and it deals differently with loss situations. The situation, which is indicated as duplicate acknowledgement, means that you receive acknowledgements from the receiver side, but these indicate that one segment has been lost. In case of a timeout, there is no reaction at all for a segment. The first situation is regarded as less severe by TCP Reno because there is timely feedback. TCP Reno concludes that the network congestion may not be that high and therefore does not perform a slow start. The data rate is only bisected and then increased again. This leads to a higher data rate in comparison to TCP Tahoe. Tahoe and Reno are TCP implementations from 1988 and 1990. In the later years, more and more TCP congestion control algorithms have been developed. Typically, the newer algorithms have advantages in some scenarios, for example large networks with huge data rates, but have disadvantages in other scenarios. In the material you find more information and links about this.